Hello students, welcome back to Math 332 Elementary Linear Algebra. In this video, we are going to introduce another operations that we can do on vectors. So we know that we can take two vectors and add them together. We can also take one vectors and one number and multiply them together. And today we are going to look at an operation called the dot products. So we can take two vectors in Rn, for example, and take the dot products of that two vectors, and it will give us a number. And that numbers, if it is 0, will tell us that the two vectors are actually orthogonal or perpendicular to each other. And these special geometrical properties of vectors being orthogonal to each other is actually pretty useful. And we are going to use that to talk about the concept of basis. Last time we know basis is a set of vectors that span the space and also linearly independent. But if we add the orthogonal property of those basis vector, it will actually simplify a lot of computations that we did from before. So we are going to investigate having all this special property, how it can help us in the computation and our conceptual development of our concept in linear algebra. All right, without further delay, let's get right to it. All right, so we are in section 3.2 and also 3.3, which is on dot products and orthogonality. And at the end of the video, you should know what is the dot products and how to apply them. And you should know what is a orthogonal set of vectors and how to apply all this concept. All right, so let's begin with the definitions. So suppose you have two vectors in Rn, right? And the dot products, sometimes also known as the Euclidean inner product, is of these two vectors is defined like this. So if you have a vectors u in R3, okay, and you have another vector v in R3, then the u dot v, that's how we say them, is defined like this, right? So you will get a number, right? So you can see that the dot products of two vectors is no longer vectors, but instead it is just a number, right? Because what we do is we take the corresponding component, multiply them together, and sum it up like this. So the dot products of two vectors in Rn is no longer vectors, okay? Now, let me ask you a quick questions right here. So if you have a matrix, all right, let's say 1, 2, 3, 4, and then another matrix 4, 5, 6, 7. What is the dot products between these two matrices? All right, if you have a polynomial 1 plus x, okay, and then another polynomial 1 plus x squared, what is the dot products between these two matrices? Okay, well, the answer is, what's the answer? The answer is we can't talk about dot product like this. I have no idea how to do dot products between two matrices and two polynomials because the dot products that you see right here is defined for vectors that is in Rn, okay? We can do some kind of inner products, which is a generalizations of dot products for stuff that looks like this, but we are not talking about it right now, okay? So pay attention to the definitions. So every time when you read a new concept, make sure in what context that particular definition is applied, right? So in this case, we are not talking about all the spaces like m by n or p2. We are not talking about all these spaces. We are basically go all the way back to the basic and talk about vectors that is in Rn. And for vectors that is in Rn, we can talk about dot products between vectors that is in Rn, and the definitions is given by this, okay? So that's the definitions. Okay, now we know what is a dot product. We can do all these computations. Easy peasy, right? So this is a vector that is in R4. This is a vector that is in R4. The dot products, as you can see, no longer give you a vector that is in R4. Instead, it will give you a numbers, all right? And if you notice that the vectors, okay, this is a vector v. If you take the dot products between this vector v and itself, so you will get this quantity. And this quantity is something that we know. This is a quantity that we see a lot. This is actually the magnitude of the vectors square, right? So remember, if you have a v, okay, so let's say it's only just like v1, v2, sorry, oops. So if you have vector v and you have component v1, v2, v3, so what's the magnitude? So the magnitude of this vector is square root of v1 squared plus v2 squared plus v3 squared. And this part right here is actually v dot v. So instead of using this square root notation, it's easier just to write everything like v square, magnitude square is v dot v. So this is like one of the first formulas, you can say, that you know about the dot product. So the dot product of vectors by itself is the magnitude of that vector's square. All right, so we have that. Okay, so now some of the property of dot products, it shouldn't be a big surprise that the dot product is commutative. U dot v is the same as v dot u, right? If you look at the definitions of how we define the dot products, you can see that u dot v and v dot u obviously is the same thing, because the component right here inside here are real numbers, and real numbers are commutative. So u1 v1 is v1 u1, so it's not a big surprise that dot products is commutative. Dot products is also distributive like this. Okay, you can distribute. This is also not a big surprise. If you wanted to verify and prove them, it's pretty straightforward. Write down your u, write down v, write down w, and do the dot products, and do the left hand side, do the right hand side, and you will see that they will be equal to each other. All right, and if you have dot products, u dot v multiply a scalar, this is the same as taking k u dot v. These are all very, very straightforward. All right, another very key observations is that if you take a vectors v by itself, okay, take the v dot itself, right, because this is what we get, right? We get the component square, right, all the way to this square. So all this thing here cannot be a negative numbers, right? So this is non-negative. V dot v is never negative. V dot v is never negative. So this is how we say it, non-negative. All right, it could be 0 though. So, and when your v dot v is equal to 0, you can see that this thing here, if you really want it equal to 0, every single component here has to be 0. That means that the vector v is 0. So v dot v, okay, is 0 if and only if the vector is 0, right? So this dot product is 0, that means this has to be 0, right? If this vector is 0, then the dot product is 0. All right, so this is one of the property for dot products. It's called a positivity property, which means that the dot products can never be negative, and it can be 0, and there's only one way it can be 0, that is when the vector itself is 0, okay? All right, now let's move on. Okay, so this is one of the example, basically just applying the dot products, okay? Basically just applying the dot products. The property, the dot product that we just see right here using this theorem. All right, so we can okay, distribute. So we can distribute. So we can distribute, right? We can distribute. So if you do that, you have u dot u, right? You have u dot v, right? You have v dot u, and we have v dot v. And u dot v and v dot u is the same, so we group them together and we have that, right? And the rest is u dot u and v dot v. So this is just a very simple example on how to apply the property, okay, that we have from the previous slide right here. Okay. All right. Now, why is the dot product so useful? All right. The reason why, one of the main reasons why dot product is so useful is that in R2 and R3, the dot products of all these vectors has something to do with the angle between the vectors. So you have a vector u, you have a vector v. This angle, all right, is connected with the dot product. Surprise, surprise. Okay, so this is given by this theorem right here that says that if you have vectors uv in R2 and R3, the theta, the angle between the two vectors, is actually given by this. So u dot v, all right, okay, equals to the magnitude of the vectors, that's the notations, multiply the magnitude of the vectors v, multiply the numbers cosine theta, okay, where theta is the angle between those two vectors. So for any vectors uv in R2 or R3, the angle theta between the vectors can be given like this. So we're not going to prove it here. The proof, if you are interested, you can just Google it, and you can also find them on in a lot of calculus textbooks, especially if you have taken Calc 3. You definitely have seen something like that before. All right, so we're not going to prove this here. We're just going to tell you that this is one of the main main important, very, very crucial application of dot product is to connect the vectors with its geometrical property, which is the angle between the two vectors. Okay. Now, so for example, computationally, if you have this vector u, you have this vector v. Let's compute the magnitude. So the magnitude of vector u is like this. The magnitude of vector v is like this. You take the u dot v turns out to be this, and you can now use this to compute the angle between that two vectors. So you can see it's very difficult to just look at u, right? 2, 2, negative 1, and then you have a v, 5, negative 3, 2. It's very difficult to see what is the angle between them. Well, the angle between them is given by this. Okay, it's roughly 84 degrees, right? So it's pretty useful. And more importantly, you might wonder, like, wait a minute, why do we have to talk about R2 and R3? It's because in R2 and R3, we can imagine it's the angle, right? But in Rn, we can't even imagine what happened in R4. So now, so in Rn, right, where your n is greater than 4 or greater than 3, which is 3, 4, 5, like all this higher dimensional space that you can't really imagine, we can still talk about the angle. We just say that, well, it should be the same. So you'll be like, okay, so if your vectors uv is in Rn, we are going to define, okay, so this concept, like what do you mean angle? So this angle here is actually a definition, okay? This angle is defined to be the inverse cosine of this quantity here, basically saying that, hey, this formula is so useful in R2 and R3, I'm going to extend it to R1000. What is R1000? Can't imagine it, but suppose we can. It should be an angle between those vectors, right? And those angle is still given by this, okay? So this is why this is definitions, okay? It's not a theorem. This is a definitions because we can't really do the proof in Rn, okay? So the angle, we can still talk about the angle, but the angle now is given by that. The key thing about the dot product is when the dot product is equal to 0. This happens when the cosine theta is equals to 90 degrees. Look at this. Look at this formula. Look at this theorem right here. You look at this. This is equal to 0, okay? If your vector u and vector v are non-zero vectors, these are non-zero, right? These are non-zero. So the only thing, if your u dot v is 0, is that your cosine theta has to be equal to 0, and your cosine theta equal to 0 when they are perpendicular to each other. That's our 90 degrees, okay? So this is critical. This is actually very critical. The two vectors u and v, all right, are orthogonal. Orthogonal, it just means perpendicular, right? It's just a fancy way of saying perpendicular, right? The two vectors are orthogonal if and only if their dot product is equal to 0. So dot product equal to 0 give you a complete classifications on the vectors being orthogonal. If you have two vectors that are perpendicular to each other, the dot product is 0. The dot product is 0, the two vectors are perpendicular to each other, right? You know, if and only if, right? This is pretty powerful, right? So for example, if we give you these two vectors in R4, all right, can't really imagine what happened, can't really sketch them, but we can still talk about the angle, right? And the dot product turns out to be 0, then we know, dude, this is easy. The two vectors is orthogonal in higher dimensional space. Yeah, I can't really imagine what R4 is, but they are orthogonal, okay? So that's that. And using the dot product, we can also have a higher dimensions Pythagoras theorem, right? We have a Pythagoras theorem that says that, hey, I don't have to be in R2 or R3. If I'm in Rn, okay, if these two vectors are orthogonal, okay, this sum squared, the magnitude of u plus v squared, is still equals to the magnitude of u squared plus the magnitude of v squared, okay? All right, so what it says is that, let's say we are in R5, okay? We still have Pythagoras theorem. This is Pythagoras theorem in higher dimensions. What it says is basically if you have a vector u, right? If you have vector v, right? They are orthogonal, okay? Orthogonal in the sense that the u dot v is equal to 0. Then what happens to u plus v, right? U plus v is this one right here, u plus v, right? If this one and this one is still orthogonal, the magnitude of this vector square is still equals to the sum of the magnitude square of these two vectors. So this is higher dimensions Pythagoras theorem. Proof is actually pretty straightforward. Proof is just very, very straightforward. Okay, what you need to do is just to compute this dot product. And we already computed before in the previous example. Okay, expand, expand, expand. And you see that this thing right here, if the dot product is equal to 0, which is 90 degrees, the dot product equal to 0, then this thing here will be this. This thing here will be this thing here will be 0, this thing here will be this. So you will have this. So you will have that this quantity square is equal to sum of these two quantities, and if and only if they are perpendicular. It's very, very straightforward. Very, very straightforward. All right, see that? Okay, very, very simple proof. So we do have Pythagoras theorem hold, right, in higher dimensional space. Okay, everything's still fine. We are okay. Pythagoras, I mean, he's going to be pretty happy. The reason why all this thing works is because we define dot products and orthogonality in higher dimensional space. Right here, we're still able to talk about the angle. Okay, we're still able to take the dot product. It's not going to be a problem. Our dot product is not defined only for R2 or R3. Our dot product here is defined for Rn. All right, so we need to be able to talk about higher dimensional space. If you're computer science, you know that your data is going to be like what? How many big data that you have? A lot. If you arrange them as vectors, you are in a lot. You have a lot of data. You're in this kind of space, and we still want to do some kind of analysis. We still want to talk about the shortest distance between two data or something like that, right? So we need to have all these concepts defined in higher dimensional space, and we can do that. No problem at all. Okay? All right. All right, another thing, in another situations we will run into dot products is when you do projections. So this is not new. You have seen it before, and this is one of the homework problem from long time ago. We talk about how do we do a projection of a vector v onto u, and I spent a lot of time deriving the formula, so I'm not going to derive it here. So you can see that you have a vector v, all right, and then you have a vector u, and you want to project the vector v onto u. So what is this vector right here? What is this vector right here? This vector right here is known as the projections of vector v onto u. And we have a formula for this, and that formula is right here. You should be able to derive it. I derived it multiple times before, and I also did it in homework and in classes. And obviously, we did it for vector that is in R2 or maybe R3. But in Rn, we still do the same thing. We just like, doesn't really matter. R2, we have this formula. R3, we have this formula. And we are going to define projections in any Rn using these formulas, okay? So that's the concept of projections. This is a very important concept too. We're going to use that a lot. So this is a time for you to review all the homework problems that we did on projection if you forgot about it. Okay, so well, you can if you still remember, you can answer all these questions. All these questions here are the questions you have seen on the homework before. So if you need to pause the video to review this, you should do that. Okay, the question right here is say find this projection of these vectors onto the line that make an angle theta with the positive x-axis. So if you still remember, this is one of the homework problems. Okay, so you have a vectors. Okay, this is a line out which make an angle theta with the positive x directions, and you have your E1 right here. All right, so you have an E1 right here. So this is an E1 right here, and you are asked to find the projections. Okay, you are asked to find the projections, okay, of this vectors E1 onto L. So how do you do that, right? We need to find this projection. Okay, so this is something that you should be able to do. We did that before. So I would like you to pause the video and think about it, okay? All right, so think about it as a reviews. Do it for you, do it for me, all right? All right, I would like you to take a moment to think about these particular problems, and you can pause the video, and when you think you already have the solutions, you can restart the video and we can look at the solutions together, okay? Okay, so I would like you to look at the solutions right here, okay? This is the solutions, This should ring a lot of bells. This is exactly the type of problem we did in homework a few weeks ago. So take a look how this is done. But the key thing is we need to be able to write down a vectors to represent the line out, and that vectors is actually given by this. So the whole question is basically said, hey, find the projection of E1s onto A, this vector A, right? Because the key problem in this particular questions here is that, whoa, look at this, This is talking about projection of a vector onto another vectors. Hey, L is not a vector, L is a line. How am I going to be able to do this problem if this is actually talking about a vector projecting to another vector? I don't have another vector, I have a line. Well, you can make a line a vector too, and that's how you do it, okay? Make sure you know what's going on, all right? Okay, so this should be something that you should know. This is just a review, okay? This is just a review, nothing really new here. All right, let's move on. Okay, so what have we learned? We learned that dot product is pretty cool. We learned that dot products can give you the angle between the two vectors. We know that when the dot product is 0, then they are orthogonal and perpendicular. Okay, so now if you are given a set of vectors, okay, this set of vectors is called orthogonal set if all of the vectors here, if you choose any two vectors, any of the two vectors, you take the dot products, you get 0 if the two vectors you're choosing are distinct. Okay, so that's what they're saying. So a set of vectors is called an orthogonal set. A set of vectors is called orthogonal set, meaning that any two vectors that is different chosen from the set, they are 90 degrees, they are perpendicular to each other. That's what this thing says, okay? It's to say in a very mathematical way, but you should be able to understand it. It says that vi dot vj will be equal to 0 whenever your I and j, the indices here, are different, okay? So for example, our standard basis, our orthogonal set, right? Think about it, right? So let's say you have R3, right? Your R3, your E1 is 1, 0, 0, right? Your E2 is 0, 1, 0, right? Your E3 is 0, 0, 1. This is a perfectly nice orthogonal set. Take this vector, they're different, right? Take the dot product, it is 0, right? Take these vectors, they are different vectors, take the dot products, they are 0. No matter how you do it, as long as you take two vectors that are different from these three vectors, you'll always get dot product equal to 0. So if you put them together in a set, that is what we call an orthogonal set, okay? So the standard basis is an orthogonal set, all right? And so something that is not so obvious is that, what about this, right? It's not so obvious. Actually, you can also see that if you take this vector, take these vectors, take the dot product, it will be 0. Take this vector, take these vectors, take the dot product, it will be 0, right? Take this vector, take the dot product, it will be 0. So again, this is also an orthogonal set in R3. So this is another example. Right, so for people who have studied discrete mathematics or like in high school, you should know that if you have 3 things, how many ways you can choose 2, right? So 3 choose 2, you have altogether 3 different ways of selecting 2 different pair of vectors, right? V1, V2, V1, V3, or V2, V3, right? So we check all of them, and they all give us 0. So this is what we say an orthogonal set, right? So this is an orthogonal set, okay? All right, what is it used for? Why do we care about orthogonal set? Okay, well, there are a lot of nice property for a set of vector being orthogonal to each other, and one of them is that if you have orthogonal sets in Rn, those vectors definitely linearly independent, right? If you have orthogonal sets of non-zero vectors, okay, careful, non-zero vectors in Rn, then all these vectors is guaranteed linearly independent. So for example, linearly independent, we know for sure. Okay, but this one is harder to see, right? It's linearly independent because they are orthogonal sets. Why is orthogonal sets give you linearly independent sets? Well, not so difficult to see either. This is the proof of the theorem. Not very difficult to see. In fact, it's pretty easy to understand what's going on here. What we do is, again, nothing fancy. We didn't do anything very, very fancy. We start from the definitions. If you have V1, V2, all the way to Vk, let's say these are orthogonal sets. We want to show that they are linearly dependent. How do we do that? Well, we set up this equation as always, right? As always. We set up this equation and we try to figure out C1, C2, all the way to CK. They all have to be 0. If they all have to be 0, and this is the only answer, then they are linearly independent, okay? So I'm going to show it to you that they are indeed has to be all 0. How do we do that? Well, okay, take this equation. Now take the dot product with VI, okay? I is any number from 1 to K. And then you distribute. You distribute, you distribute, you distribute. This is what happened after you distribute, right? Okay, so this is distributing. Here is the VI dot 0. VI dot 0 is the number 0. By the way, this 0 here is a 0 vectors. Be careful about all this notation right here. So you have a 0 right here, and the left-hand side, you distribute. You distribute, and you can see that if your I is different from 1, this is 0. If I is different from 2, this is 0. If I is different from K, this is 0. The only terms that survive here, is the I terms. Do you see that? If your I is different from 1, this is 0. If your I is different from 2, this is 0. The only terms that survive on the left-hand side is the VI. And you have CI, VI dot VI. This is the only terms that survive. Okay? The rest of it, they are all 0. Why? Why? Because, take a look. That's a hypothesis. These are orthogonal sets, right? So if you have I, this I is different from 1, then VI dot 1, 0. If this I is different from 3, then VI dot 3 is equal to 0. It's very easy to see that. So the entire left-hand side will be all dead. The only surviving terms is this one. All right? And our VI is not a 0 vectors, right? Remember in the very beginning, VI dot VI is always non-negative. And VI dot VI can only be 0 if and only if your VI is 0. If and only if your VI is 0. But you look, take a look. These are non-zero vectors. So your VI is non-zero vectors, which means this dot product is a non-zero numbers. So you have CI multiply a non-zero number, you get 0. Your CI must be 0. Right? So you take VI, take the dot product of VI with all this thing, you will get CI equal to 0. So you do it one by one. You dot it with V1, right? You get C1 0. You dot it with V2, you get C2 0. At the end, at the very, very end, you dot it with VK, right? You get CK equal to 0. So actually, this system right here, right? The only solutions is all the coefficient has to be 0. What does that mean? It means that all these vectors right here, they are linearly independent. As simple as that. So you can see orthogonal sets are good. Orthogonal sets immediately give you linear independence. That's pretty good. And now, because they are so good, we can also talk about orthogonal basis. Right? Orthogonal basis is a basis, just like usual, but we require that all the vectors inside has to be orthogonal as well. So for example, okay, these vectors are actually orthogonal. It's an orthogonal basis. Why? Because they are linearly independent, okay? Right? Because these are, if we check, these are orthogonal. Orthogonal means linearly independent. And 3 linearly independents in R3 will form a basis. This is one of the orthogonal bases. All right? Okay, this is one example of orthogonal basis. Why do we not checking the span? Because I'm using a theorem here. There's a theorem that says that if you are in R3, if you know the dimension is 3 and you can find 3 linearly independent vectors, then the span is definitely going to happen. This is going to be a basis. Okay? Now, let's look at another theorem. Okay, if this is moving too fast, pause. Okay? And then go take a walk and then come back. All right. Now, remember, okay, that last time, if you have a basis, right, all this component here, right, is going to be unique, right? All this scalar is going to be unique. This scalar is actually known as the coordinates, right? And computing the coordinate could be a little bit tricky, but if your vectors here are orthogonal basis, okay, if you are orthogonal basis, all this coefficient here is very easy to compute. In fact, it is given by these formulas. And why is it so? Not difficult at all, right? So again, this is an orthogonal basis, right? So if you have W, right, W will be written like this because it's a basis. So everything is spanned by all the components in the basis. So once you have this, you take a dot product with VI. Again, everything that is not related to VI will die. And the only thing that survives is against CI. So what is CI, VI, VI? CI, VI, VI is equal to this. So what is CI? You divide, okay, and you will get this. So all these components, all these coefficients here are very easy to compute if your bases are orthogonal. If your bases are orthogonal, okay? So for example, right here, all right, W is this. This is a V1, V2, and V3, right? Find this coordinate with respect to this basis. How do you do that? You might want to pause this video and think about it. You might want to pause this video and think about it. Review a little bit what's happening here. Make sure you understand it. Make sure you understand it and give it a try, okay? All right, so I want you to pause the videos and give yourself some time to think about the problems. And when you think you are ready and have the solutions, you can resume the videos and see whether or not your answer is correct. All right, so the solution is actually pretty straightforward, right? Using this, I think you can appreciate it, that if you want to find the coordinates, we need to know all this coefficient, right? If you want to know the coordinates with respect to that basis, the coordinates are all given by all this coefficient. And we know how to compute all these coefficients if your V here are orthogonal, okay? Orthogonal. Okay, Vi dot V2 equal to 0, Vi dot V3 equal to 0, V2 dot V3 equal to 0. If you have that, your C1, C2, and C3 is easily obtained. You don't have to do row reduction whatsoever. You just take the dot products and you will see that that W will be 1/6 of this, 5/2 of this, 2/3 of this. That is the now our coordinate with respect to V1, V2, and V3. Okay, now one last thing, okay? We just want to make our life much more easier. So instead of talking about orthogonal, there's another concept called orthonormal. Orthonormal is not so bad. First of all, it has to be orthogonal. Second of all, you want it to be a unit vectors. So this is orthogonal vectors, this two here, right? Okay, 1, -1, 1, right? 1, 2, 1. These two vectors are orthogonal of each other. Right, let's take a dot product. The dot product is going to be 1 minus 2 plus 1, which is 0. They're orthogonal. But this is not a unit vectors. Okay, this is also not a unit vectors. So we normalize it. Okay, it has a length square root of 3, so we divide that. So this is a normal vectors. Sorry, this is a unit vectors. Okay, this one here, what is the magnitude? How big is this vectors? This vectors here, the magnitude is square root of 6, so you divide it by square root of 6. So this is now a unit vectors. So this is your unit vectors. So if you take the orthogonal vectors and normalize it, then we form orthonormal vectors, right? Orthonormal vectors. So orthonormal vectors is just what we know from before, and now it is normalized. Why do we want to do that? We have nothing better to do. Well, it's because if you do that, then Q1 dot Q2 is 0, obviously, because they are orthogonal. But then Q1 dot Q1, we know for sure is 1 because it's unit vectors, right? So we know that Q dot Q, actually any vectors, right? V dot V, you still remember V dot V is the magnitude of V square, but this is 1. 1 square is 1, so it gives us a slightly nicer property. And everything your computation that you did last time, this computation you did last time will be easier. Okay, that's the only things that we talk about, because if there are orthonormal bases, your C1 and C2 and all that, have a slightly better formulas, right? Remember, like last time, you look at this one, your C1, C2, it look a little bit messy, but now the VI dot VI is 1, so things get simplified a little bit, and you don't have the WI dot WI, QI dot QI stuff, Q1 dot Q1 stuff is all 0. So you have that. You have this representation now. It's just nothing better to do and make it slightly better. Okay? It's not very complicated. All right? So what is the key thing here that you need to remember? Well, dot products. Why dot products is important? It gives us the angle between the two vectors. And when they are perpendicular, the dot product is 0, and everything is nice, because when you have orthogonality, apparently you have a set of vectors that are orthogonal to each other, they are definitely independent. They are definitely linearly independent. And if you put them as a basis, it's very easy for us to write the coordinates. We don't have to do row reductions. We just dot, 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 and dot. And that's it, okay? All right, so this is like the basics application of dot product. Okay. All right, this is the end of the presentations. And the next video, we are actually going to look at something that is slightly more conceptually challenging, but not so bad. Those concepts are known as the orthogonal complements and orthogonal projections. As you can see, we are starting to exploit the property, okay, the property of orthogonality, and we are going to do it for quite some time. Actually, we are going to do it all the way until we develop a method called the least square methods, and that will be kind of like end of the semester. So from now on, the concept of orthogonality is going to be our bread and butter. Okay, so I hope you are ready and take on this new challenge, and it's going to be fun. All right, let's just see you in the next video.